Welcome to a screencast on enthalpies of formation and reaction enthalpies. To start, let's consider a few thermochemical reaction equations, and the first one is the reaction of nitrogen and hydrogen to make hydrazine, N2H4. The next one is iron and oxygen reacting to make iron 3 oxide, Fe2O3, and the third is carbon, hydrogen, and oxygen reacting to make glucose, C6H12O6. Now, a couple things to note about all three of these thermochemical equations. In each case, we have elements reacting to make a compound. More specifically, we have the constituent elements in their normal or standard states reacting to make 1 mole of the compound. And when the constituent elements in their standard states react to make 1 mole of the compound, there is a delta H value associated with that process. So in each reaction above, we have a compound, 1 mole of the compound, being formed from its constituent elements in their standard states. Now, this type of reaction, forming a compound from the constituent elements in their standard states, is very useful to us, and the delta H for this type of reaction is what is known as a standard enthalpy of formation, so symbolized by delta H sub F, where delta H is enthalpy change, so it's the enthalpy change for this reaction. The subscript F stands for formation, the superscript 0 stands for standard states, and this is always going to be making 1 mole of that compound, and so this is a standard enthalpy of formation. Now, this is very useful, and because of that, standard enthalpies of formation are found in tables in chemistry textbooks, they're in reference books, they're very useful for all kinds of different thermochemical calculations, and here are just a few example delta H of formations. And for example, with the CO2, the delta H of formation is negative 393.5 kilojoules per mole. And what this means is when carbon and oxygen in their standard states react to make 1 mole of carbon dioxide gas, 393.5 kilojoules are given off. Similarly, we have some delta H of formation for some other compounds. And for example, hydrazine has a delta H of positive 95.4 kilojoules per mole, and that means when nitrogen and hydrogen in their standard states react to make 1 mole of hydrazine, it takes 95.4 kilojoules, or 95.4 kilojoules of energy are absorbed. Okay, now why are these useful? How can we use delta H of formation? And it turns out for any chemical reaction, and just as a side note, this can be shown to be the case. A little bit of a description of this is given in the Hess's Law screencast. But basically, because enthalpy is what's known as a state function, it turns out that the enthalpy change for a reaction can be calculated from the enthalpies of formation of the products and reactants. And specifically, the delta H for any chemical reaction will be the sum of the delta H of formation of the products times their stoichiometric coefficients minus the sum of the delta H of formation of the reactants times their stoichiometric coefficients. So here in this equation, the letter sigma stands for sum, so we're adding up all of the delta H of formations of the products. N is the stoichiometric coefficient for that particular, in this case, product. And delta H of formation, of course, is the enthalpies of formation, which we can often look up in tables. Now, this is probably easiest to see by an example, so let's use enthalpies of formation to calculate the delta H for the reaction of C3H8 propane reacting with oxygen to make CO2 and H2O. In other words, complete combustion of propane. Well, from the table, We can find the delta H of formation of propane, negative 103.8 kilojoules per mole. Oxygen may be listed in the table, but even if it isn't, oxygen is the element already in its standard state if it's O2 as a gas. So no energy is needed, no heat is needed to take oxygen in its normal state and make it oxygen in its normal state. So the delta H of formation of any element in its standard state will be 0. CO2, we saw this before, has a delta H of formation of negative 393.5 kilojoules per mole. And then water liquid is negative 285.8 kilojoules per mole. And I'm using liquid here rather than gas because at 25 degrees Celsius, the water that was produced by the combustion, maybe as steam because it was hot, is now liquid once it has come back to room temperature. Okay, so our equation is delta H of reaction is going to be the sum of the delta H of formation of the products times their coefficients. So that would be 3, coefficient for CO2, times negative 393.5, plus 4, coefficient for H2O, times negative 285.8. And then we subtract the delta H of formation of each of the reactants times their coefficients. Propane C3H8, negative 103.2, and then 5 times 0 for oxygen. And then it's simply do the calculation, and in this case the result is negative 2,220.2 kilojoules. So that would be the delta H of reaction for the complete combustion of propane as written. Now one last note. If you know the delta H of formation of all the substances in the chemical reaction, you can of course add them up and subtract and get the overall delta H. But also, if we know a delta H for a reaction and we know all but one of the delta H of formation, then we could also solve for that delta H of formation, and that is sometimes how delta H of formation values are determined. So that is it for the enthalpies of formation and reaction enthalpies screencast.